Hi everyone. So in this video we will be going through the topic of definitions of Reynolds number. And the idea behind this video is to sort of give you a flavor of different definitions of Reynolds number that we have already discussed. And sometimes there is confusion about what should be the right definition of Reynolds number, uh, and there might be sometimes confusion as to why we chose this length scale and why we chose this velocity scale. So basically this video is kind of a refresher for us to discuss different cases we have discussed till date about Reynolds number, and then to sort of uh, show you how our definition of Reynolds number is important, and how that actually changes the way we look at the problem. Okay, so let's start first with the definition of Reynolds number. So Reynolds number is defined as a density scale, a velocity scale, a length scale, and a viscosity scale, right? So this is how we define Reynolds number, and that is how we did in the lecture. Just to give you a little bit of feeling of how we can think about Reynolds number, we can write this as rho u square divided by mu u by L, right? So you can imagine that this is something we have discussed in class, that rho u square is kind of a inertial stress, right? Inertial stress, and mu u by L is kind of a viscous stress. So Reynolds number is basically a ratio of inertial stress by viscous stress. So again, this is something we have discussed several times, but just to sort of refresh that what we're doing. So once we know the fluid, we will know the density and we will know the viscosity. What we will need to define is this velocity and length. And it is important for us to sort of understand how to in which case which velocity to use, which length scale to use. Okay, so we will discuss that in this video. So let us go back. We'll just basically start discussing cases that we have already discussed and just sort of go step by step. So remember, the first case we discussed was pipe flow, where we had a length L, diameter D, and we were flowing a fluid of density rho, viscosity mu, and velocity u average. Okay, now so we have to define a Reynolds number. Now we know that density is rho and viscosity is mu. So this is pretty straightforward. We can just write rho here and mu here. What we need to now define is this velocity scale and length scale. Okay, so velocity is probably pretty intuitive that we will use u average, because that is a very good characteristic velocity scale to take. It's an average velocity scale and we can take that. But what should we choose as length? Should we choose the length scale as the diameter of the pipe, or so the length of the pipe, or the diameter of the pipe? So we have two options, whether we should choose this or whether we should choose this. And as you can recall, we chose diameter in the case of pipe flow. Now, why should we choose diameter? Is there any logic behind choosing diameter, or is it just a random choice? So in this case, diameter has a significance of why we are using that. So you can imagine now, because we have discussed velocity profiles, we have discussed Navier-Stokes equation, and we have solved this problem in our class. So you already know that the stress which actually acts, so let me just name the coordinate system Z here and R in this direction. You can recall that the stretch which is active is actually tau RZ, which is given by mu del VZ by del R, right? This is something we have discussed in class, that the active stress, the shear stress, active stress is on the velocity component in Z direction, because the velocity component is only in Z direction, and with respect to a derivative in R direction. Now, when we define the viscous stress here, we use a velocity scale and a length scale here, over this viscous stress will act, and that's why the viscous stress will act in this direction of R, and diameter is the scale, or radius can also be the scale, but in this case we choose diameter. Okay, so yes, so we can define a Reynolds number like rho u average d by mu, but we choose diameter as the length scale and not the length of the pipe, and because the viscous stresses act in this direction. Okay, so I hope that this sort of made sense. There is some sort of understanding of why we chose diameter and not the length. Okay, this is an important sort of understanding. So basically, this tells us that in the Reynolds number we are not including the length of the pipe, and which is helpful to sort of get a physical feeling of why we choose diameter over length. Okay, so now let us get to the second case that we discussed in class. So this was discussed in chapter 2, as you may remember, pipe flows. And then what we did was we discussed friction factor versus Reynolds number. And you can also recall that we went from the whole Navier-Stokes equation and we discussed how we can derive for laminar flow friction factor versus Reynolds number. Just to refresh your memory that this is something we discussed in chapter 2. And then we also went back, revisited this using Navier-Stokes equation in chapter 7, chapter 7. Okay, so now let's go and talk about the second case we discussed, which is flow around object. So we had again we had the diameter of the sphere D, and we were flowing some fluid around this with viscosity rho, density rho, viscosity mu, and velocity u average. Right, so diameter D, and the flow will go around this, and we know that this will be some drag which this will experience. So we defined again a Reynolds number here, one of the critical dimensionless number, and we can again use start from rho, u, rho and mu, and we have u average. Now what should we choose as the length scale here? Now length scale here, actually there is one length scale which is length scale of this sphere, and there is no other length scale available to us, and the other length scale can be, one can say, is basically infinity, right? Because the flow will happen is unbounded and will actually happen throughout. There is no bounding of the flow. So why should I use D and not, why is the D relevant length scale here? So you can imagine that when we write viscous stresses in this case, so this is something we have again discussed in class when we calculated the pressure force and the shear force, as you may remember. So when we calculate drag, or we want to associate some drag force, then we used the tau r theta drag in this case, and the in which case again you will see that basically the way we define tau r theta was mu, I mean I'm just scaling that as v theta by r. You can check that we'll scale this as some velocity in theta direction over the radius of this sphere. So that's why the way we scale stresses in shear stress is important, and in this case it is also based on this r, and naturally we cannot use infinity because then Reynolds number will always be infinity. And again there is a physical feeling behind of why we choose the diameter here, and that's why we define rho u average d by mu for Reynolds number. So I hope that there is some sort of understanding of why we are choosing this. Then the third thing we discussed was a packed bed. So this was chapter 3, and now this is also chapter 3, packed bed, where we had a length here, an area wetted here, and then we used this as a diameter, and there was some packing fraction epsilon, void fraction epsilon, right? And the way we define Reynolds number, and I hope you can remember this, there was also an exam problem on this, was using hydraulic diameter dh, right? And the way we were doing was that we were comparing this to a pipe flow which has a diameter of dh. So naturally the diameter dh is logical here because we were comparing this to a pipe flow, and the equivalent diameter in that pipe flow was the hydraulic diameter. So this is kind of obvious once you understand in the pipe flow why we choose hydraulic diameter and not why we choose diameter and not length. Similarly, in packed bed we choose hydraulic diameter and not the length of the packed bed because we are comparing this to an equivalent pipe flow. Okay, so just I hope that this also makes sense, and just recall that diameter was some function of the diameter of these particles and epsilon. Again, there was an exam problem which everyone did very well. So hopefully everyone understands this concept that we can find hydraulic diameter based on the knowledge of this diameter of this and the packing fraction, or we also made cylindrical particles and you can find the hydraulic diameter based on that. So just to recap again what we have discussed, we are discussing Reynolds number with which is rho u L by mu, and trying to understand velocity scale and length scale. Velocity was pretty obvious here, and a length is generally has been the topic of more discussion, where we have been basically discussing for pipe flows why diameter is more important. That is where the stress which is important is tau rz. So the delta r is diameter, that is why it's important. Similarly here it is tau r theta, and there also the length scale is correctly it's the diameter of this sphere. And then packed bed is basically the same as pipe flow because we just changed the system into a pipe flow with the equivalent hydraulic diameter. Okay, now let's keep moving. So this is chapter 3, and then we went into hydrostatics and then more into Navier-Stokes derivation. So we did not discuss Reynolds number for a while, then we came back to pipe flow, which we have already discussed. Then we started going into this nearly unidirectional flow, and here is sometimes where students get confused, right? And we have u average, rho mu u average. Reynolds number. What will be Reynolds number here? So one way you can define Reynolds number is rho u average h naught by mu, right? Or you can also define using hl by mu. Both are fine, but the important direction is that it should be h and not length, because again the stresses which will be important if this is x and this is y, the stress which will be important will be tau xy. So that is this is the one which is perpendicular to x, that is this on this surface pointing in this direction, and this surface is perpendicular to x, so that's what tau xy, and again which will be mu u average by h. You can choose h naught or hl, but you will not use the length of the uh, the tapered channel. So this was nearly unidirectional tapered channel, but not the length of the channel as your dimension as your length scale. Okay, so hopefully this also makes sense. Now fifth point is somewhat a bit confusing, and this is also something we gave in the exam 2, was when we had a porous plate here. Porous plate, this was the porous plate, and this was a solid plate, and h was this, and this was u as a function of time, and we were saying that the flow goes out from here, and this is length L, let's say. So what should be the Reynolds number? So the way the Reynolds number was defined was rho ut ht by mu in the problem, and what we realized was that a lot of students did not sort of understand that this Reynolds number is different than Reynolds number. So let's say this is x and this is y. So this was Reynolds number. This may not be the most appropriate Reynolds number definition for a problem. However, because we know the velocity in y direction and we know the length in this direction, we just chose this as the Reynolds number. Let's call this as a function of time. We just define this as rho ut ht by mu. If we go by the logic of the way we were defining the Reynolds number till now, we should write this as a Reynolds number velocity in x direction, because this is the velocity which we care about, the main velocity of flow going from porous plate flowing out like this, right, times height by mu. Because height, because again the stress we will care about is tau xy, right, because this should be shear stress acting on this plate or this plate and pointing in, so yeah, perpendicular to x and pointing, sorry, so my mistake, this was actually tau yx here, so I'm sorry, this was tau yx, this was perpendicular to y and pointing in x direction. Similarly, this was tau yx here, tau yx, so please correct this was tau yx, both of these cases, perpendicular to y and pointing in x direction. and that will still have mu, basically ux by h, right? So this is the most appropriate length scale, but these two Reynolds number are not the same. So when students performed order of magnitude analysis, they forgot that this Reynolds number is not the same as this, and they just used Re prime, which I'm defining here as rho ux h t by mu, as the same as Reynolds number that was given in the problem. So you can convert between these two Reynolds number, and I understand that this is a more representative Reynolds number because of the cases we discussed, that the velocity should be in x direction and height is is the right tau because of tau yx. But if you are given something like this, you can easily convert between these two. So students did correctly. Almost all of the students did correctly that they found the right by doing order of magnitude analysis. This was a number which is coming out, but they did not convert between these two numbers. So just recall the definition of Reynolds number, the way we define in the problem, is important. So if you find something like this, you can just convert between these two. This ut was the velocity in the y direction, and ux is the velocity in the x direction. So ut was the velocity scale in the y direction, and ux is the velocity scale in the x direction. And to convert between this, you can use continuity equation to convert from velocity in the y to velocity in the x, and then you can define Re prime in functions of Re. So that was where we saw mistakes, and we feel it is important. So this is the most appropriate Reynolds number, but the way it was defined in the problem was like this. So you can convert it into this using order of magnitude analysis. So I hope that this is making sense. So what we are trying to say is that whenever you are trying to define a Reynolds number, you have to use the right velocity scale and the right length scale. And in the case of pipe, it was B, because that is where the viscous stresses basically change in that direction. Similarly, in the case of flow around a sphere, and the case of packed bed was just similar to a pipe. The case of flow in the tapered channel, again the stresses decay in the direction, change in the direction of y, and just again this was tau yx, stress happening in the x direction, force is in the x direction but perpendicular to a surface with normal in y direction, tau yx. And again here the right was h naught, right? Because, or we can use hl also, but we have to choose something in the y direction because there is where the stress is decaying. In this problem of a porous plate, we gave her a definition of Reynolds number, which was probably not the most appropriate, but sometimes the problem defines Reynolds number in a certain way, but you can convert. So this is the most appropriate Reynolds number definition, but you can convert, and you have to realize that ux is not the same as ut. So the way you define Reynolds number, you should choose the right length scale and the velocity scale. So that is, I hope that is clear. So I'll close the video by the last topic, which is the boundary layer case, which you are doing now, which was that velocity is flowing here, u average, rho and mu, right? And the length of the plate is L, and here we have delta of x, right? So here Reynolds number is defined as rho u L by mu, as you are discussing these days in class, rho u average by L by mu. The way we have been discussing the problem till now, and somebody should definitely think about this thing, that this is actually u average delta by mu. Delta is again this boundary layer thickness, because this is where delta is the right length scale, where the delta is in this direction, that there is where the stresses are decaying. So we have been looking at this for several times now, that this will be tau yx, which will be mu u average by delta of x, right? And if somebody defines it, this is perfectly fine. In fact, this is probably the more appropriate definition. However, because of historical reasons, this Reynolds number was defined on the basis of the length of this blade, and you can convert between these two Reynolds numbers. Like I was saying, you can convert between these two numbers. And if you look in the book, in chapter 3, when we discuss a laminar boundary layer, the book also talks about that you can actually change the length scale, and that the boundary layer thickness is actually the more appropriate length scale, but just because historically it has been defined like this, people use this definition. Okay, but you can very well use the definition of delta, just that you have to use You have to interchange. So you cannot use a correlation which was defined for Reynolds number with definition L, and if you're defining definition with respect to delta. And if you cannot choose a correlation defined for delta, defined as a definition of delta for using L, you have to interchange correctly. Similarly here you have to interchange correctly between these two definitions. Okay. So hopefully this gave a good overview of the Reynolds number we have discussed. So Reynolds number is the ratio of inertial stress to viscous stress. Choosing the right velocity scale and length scale is important. The way we choose the length scale is by looking at the which stresses will be important, and you can from there you can see in which direction is the velocity changing, and you can use that direction. So in velocity changes in the R direction, so we use diameter. Velocity changes in the R direction, so we use diameter. Here it was just the pipe flow case. Then the velocity changes in the Y direction, so we use H naught, or we can also use HL. Here the velocity changes in the Y direction, so we will use the velocity in the X direction and the distance in the Y direction. But because the problem said velocity also in the Y direction, we can interchange between the two using order of magnitude analysis and continuity equation. Similarly, for a flat plate or a bond layer case, the more appropriate definition would be velocity in the X direction, which is changing in the Y direction, delta M, because we want to scale tau YX. However, historically it has been used length of the flat plate has been used as the scale, so we can convert between two again using continuity equation. So hopefully this will, and also Navier-Stokes equation. So as you will see that there is a relationship between delta and L, which goes as Reynolds number to the power of minus half. So, and Reynolds number is this RE. So you can use to go from RE to RE prime using this definition. So hopefully that this gave you a good sense and good feeling of how we can convert between different Reynolds number and which length scale is more appropriate. And sometimes if not the best appropriate scale is not chosen, you can interchange between the different definitions. So hope this video was useful, and feel free to give us any feedback, and see you in the next video.